At 7,970 feet above sea level, on a knife-edge ridge between two Andean peaks, sits a city that shouldn't exist, Machu Picchu. Roughly 200 structures built from granite blocks, some weighing more than 50 tons, are fitted together so precisely that 5 centuries later you cannot slide a knife blade between them. No mortar, no iron tools, no written language to coordinate the work, and yet the NCA built it. The question that has baffled engineers, archaeologists, and geologists for over a century is devastatingly simple. How? This is not a mystery because we have no theories. It is a mystery because every explanation we possess seems individually plausible, yet collectively inadequate to account for what stands before us. The puzzle begins with location. Machu Picchu perches on a narrow saddle of rock 2,000 feet above the Urubamba River Gorge, and it is exposed to 2,000 millimeters of annual rainfall in a region that experiences regular earthquakes. The surrounding mountainsides show fresh landslide scars. Machu Picchu's 500-year-old terraces remain intact. Civil engineer Kenneth Wright spent over 15 years studying the site, and what he discovered was striking. 60% of the total construction effort lies underground. Deep foundations, crushed rock drainage layers, and subsurface channels invisible to visitors. This hidden infrastructure is what has kept the citadel standing. Wright concluded bluntly that without good drainage, there would be no Machu Picchu today. The Inca accomplished all of this between roughly 1420 AD and 1530 AD using hammerstones, bronze chisels, and organized human labor. In 2019, geologist Rualdo Menegot revealed something unexpected. The site was deliberately built at the intersection of two major geological fault lines, forming an X-shaped pattern beneath the ridge. Far from reckless, this was strategic genius. The fault fractures had already cracked the granite into manageable blocks, dramatically reducing quarrying energy. The same fractures channeled rainwater underground, creating the perennial spring that feeds the city's water supply. The Inca did not fight the geology. They exploited it with a sophistication that suggests an engineering tradition far more advanced than we have credited them with. The stones themselves present the first technical mystery. Granite is one of Earth's hardest building materials. The Inca shaped it using river cobblestones, hammerstones made of dolerite and quartzite, selected because they were harder than the granite itself. Jean-Pierre Pratzen of UC Berkeley conducted the definitive experimental archaeology on Inca stonecutting. His process revealed a methodical approach. Large hammerstones pounded rough shapes through a technique Pratzen called nibbling. Progressively smaller hammerstones refined the form. The fitting process was trial and error. A stone was lowered into position, contact points identified by compressed dust markings. Then the stone was lifted out and high spots pounded away. This cycle repeated until the fit was seamless. Pratzen demonstrated that stones can be cut and fitted in just hours. However, he acknowledged a critical gap. His method could not explain how stones weighing over 100 tons were manipulated during fitting, which requires repeatedly raising and lowering massive blocks with precision. The results are extraordinary. In the finest walls, joints between stones measure fractions of a millimeter. They are so tight that a knife blade cannot be inserted between them. Unfinished sections near the Temple of Three Windows, where stones sit mid-shaping with smaller rocks wedged underneath, provide a frozen snapshot of the process in action. The stones tell us how they were made. What they do not tell us is how such precision was achieved at scale. Hydraulic engineering may be Machu Picchu's most remarkable achievement. The entire city layout was determined by a single natural spring, fed by rainfall percolating through fault-fractured rock. The Inca built a 749-meter stone-lined canal at a precisely calculated 3% gradient to carry water from this spring to the urban sector. Within the city, 16 stone fountains cascade through the urban sector across a 26-meter vertical drop. Fountain number 1 serves the emperor's residence. Pachacuti received the purest first-use water. Each fountain features stone spouts shaped precisely for traditional Inca water vessels. Water was not merely functional. It was ceremonial, political, engineered theater. The drainage system comprises 8 integrated components working in concert. More than 130 drainage holes are built into the original walls. Every drainage hole was planned during initial construction. None were afterthoughts. Each of the roughly 700 terraces is a multi-layered engineered system. Large stones sit at the bottom for stability, followed by gravel and broken rock, then sandy material, topped with about 1 meter of rich topsoil. This layering ensures percolation without waterlogging and prevents erosion during extreme rainfall. Wright's team documented a system that rivals modern systems. The seismic story may be the most dramatic element. Research by Carlos Benavente Escobar found that a magnitude 6.5 or greater earthquake struck during construction around 1450 AD, damaging the Temple of the Sun. This event triggered a fundamental transformation in Inca building methods. After it, they developed the signature Inca anti-seismic toolkit: trapezoidal doorways and windows, wider at the base, narrower at the top, inward-leaning walls that lower the center of gravity, polygonal interlocking masonry that distributes stress across multiple contact points. The result is what engineers call the dancing stones phenomenon. During seismic events, the precisely fitted blocks shift and sway with the Earth's motion, absorbing energy through controlled movement. When the shaking stops, the stones settle back into their original positions. Yale archaeologist Richard Berger noted the telling contrast. When there is an earthquake, only the restorations fall. The mainstream archaeological consensus holds that Machu Picchu was built through hammerstone quarrying, trial and error stone fitting, organized mass labor via the MITS system, and transport using ropes, wooden rollers, and earthen ramps. All of this is supported by physical evidence and experimental archaeology. Yet alternative theories persist. The stone softening hypothesis, that the Inca possessed a plant-derived liquid capable of softening granite, remains unverified and faces a devastating logical objection. If stones could be liquefied, why quarry and haul massive megaliths at all? Joseph Davidovits has proposed that some stones were cast from crushed rock mixed with organic binders, essentially ancient concrete. However, this does not apply to Machu Picchu, where unfinished quarry stones clearly show conventional extraction methods. The most significant modern test came during PBS Nova's 1997 special. At Ollantaytambo, 250 villagers moved a genuine 15-ton Inca block up an incline. These experiments demonstrated feasibility, but they also revealed critical requirements: prepared roadbeds, squared stone shapes, and massive coordinated labor. Yet significant gaps remain. The finest ashlar masonry has never been fully replicated in modern experiments using only period-appropriate tools. The logistical mystery also endures. At Ollantaytambo, Pratzen calculated that moving the largest stone, approximately 140 metric tons, would require roughly 2,400 workers pulling simultaneously. But the ramp was only 8 meters wide. How that many people coordinated on such a narrow path remains an unsolved puzzle. What remains genuinely mysterious falls into 5 categories. First, the finest precision. Sub-millimeter stone fitting has not been fully replicated by modern experimenters. Second, the organizational intelligence. Coordinating thousands of rotating workers at altitude without written language represents a form of project management we cannot fully reconstruct. Third, the astronomical alignments. How Inca engineers achieved fractions of a degree celestial accuracy without known surveying instruments remains poorly understood. Fourth, the speed of construction, building 200 structures, 700 terraces, and the entire subsurface infrastructure in roughly 30 to 80 years, while simultaneously constructing an empire-wide road system, implies an organizational capacity that strains credulity. Fifth, what lies hidden. Ground-penetrating radar has revealed sealed chambers beneath the visible site, and significant areas remain unexcavated. Ed Frankomont articulated it during Nova's filming. The Incas had none of the things that we think of as the prerequisites for a major civilization. No arch, no wheel, no codified mathematics. They couldn't write, and yet they could do this amazing engineering. The true enigma of Machu Picchu is not that we cannot imagine how it was built. It is that every explanation we possess is individually plausible, yet collectively inadequate to account for the speed, scale, precision, and and sophistication of the result. The gap between the simplicity of the tools and the brilliance of the outcome is where the mystery lives, and perhaps where it will always live.